This is the continued commentary for the acetal, ketal, and carbohydrate slides commentary. So, we previously discussed about enantiomers. These are the non-superimposable mirror image stereoisomers. So these ones right here. Now, we also talked about different ways of representing them via sketch. So we have two types of sketching schemes. The first one is wedge-dash structure. And then the next one is, going forward a bit, the Fisher projection. So, starting here, we now need to go ahead and figure out which type of enantiomer we have, if it's an enantiomer to begin with. So we can either have the D chiral form, as they say, or we can have the L chiral form, as they say. So, a D form is one type of orientation. So circling this molecule right here, it's one type of orientation around the chiral carbon. And the L form is the opposite form of rotation. So what I'm going to do is I'm going to give you a wedge-dash structure or Fisher projection. So I'll give you one of these two right here. And you'll be asked to identify, is it the D enantiomer or is it the L enantiomer? These are the rules down here for explaining whether we have a D or L. But before we do this, we first need to double check that it can be an enantiomer to begin with. So, is there a, as I highlight this, is there a chiral carbon that's present? So in this wedge-dash structure right here, is there a chiral carbon that's present? In this case, yes, there is, because there's 4 different groups surrounding the this particular carbon that's directly attached to this carbon. Can there be a mirror image formed off of this molecule? Yes, there is. So, let's go ahead and move on and investigate how to name it D or L. So, using a wedge-dash molecule, I have here, first thing we need to do is rank from highest to lowest priority. The highest priority is the group which has the highest atomic number. So highest atomic number. So let me go ahead and highlight this part right here. The highest atomic number. The second highest priority has the second highest atomic number, and so forth. So let's go ahead and see this on a white screen. So in this case right here, we have a carbon, and I'll go ahead and I'll create a wedge-dash carbon. A wedge-dash carbon here. Here we have a hydrogen. Here we have a hydroxide. Here we have a chlorine. And here we have a fluorine. Now, yes, there is a chiral carbon. Yes, it can form a mirror image. So now we need to figure out, is it D or is it L? D stands for dextro, and its overall groups would be orientated going to the right. L, on the other hand, stands for levo, and the groups would be orientated going to the left. D you can think of as being clockwise. L you can think of as counterclockwise. So we want to know, are each of the groups around there orientated in a clockwise or counterclockwise, which we summarize as D and L, spatial orientations. So the first thing we need to do is go ahead and, well, let me go ahead and make some corrections on this one because I noticed there's a mistake. So let me go ahead and fix that really quick. So the top one should have a dash like this. The bottom one is missing a bond to begin with, so I'll put in a dash here. Let me go ahead and strengthen these wedges. So here we have these nice wedges right here. Now, of these four groups, which one has the highest atomic number? And we're going to look at the atoms that are directly attached. So this hydrogen right here, at this point we ignore this hydrogen. We're looking at the ones that are directly attached. So in this case, chlorine would have the highest atomic number. Looking at our periodic table, so this would be the highest. The second highest atomic number would be fluorine. And finally, the third highest would be oxygen. So in this case right here, using this structure, I'm going to go ahead and use a blue pen. We would start off with chlorine and we would connect the dots. We would go this way, we go all the way down to fluorine and go to oxygen. So in this case, we're going to the left or counterclockwise. So to start us off, it looks like we would be going in the L direction. Now, if you continue to follow the rules, it now says, hey, which one is the lowest priority? It turns out this hydrogen that's directly attached is the lowest priority. And if you look at the rules, it says if the lowest priority is going into the paper and it's a dash, so it's either a line or a dash, so it's parallel or going in, then we keep this L. On the other hand, if it says that the lowest priority is forming a wedge, then we have to flip it to its opposite chiral form, in which case the opposite form is going to go from a L to a D. An L to a D. So, in this case, this would be the proper labeling of our enantiomer. This is a D enantiomer. Usually we give the name of the molecule and we put the D in front. So, going to this example right here, I need to figure out, is this particular molecule a D or L? And the highest priority right here would be an oxygen. The next highest priority would be this particular carbon. And then the third highest priority would be this carbon. And then we would be going, in this case, counterclockwise, and counterclockwise is L. However, we now have to look at the lowest priority. If the lowest priority group is going in, such as a dash or it's a line, a line would be on the same plane as the paper or screen, then we keep the L. If, however, it's a wedge, then we have to flip this particular L that I'm now circling. And I'm going to flip it from an L to a D. So this letter would be placed in front of the name, and it would be D, glyceraldehyde. Now, there's something on here which is correct, but can be a little bit confusing depending on how you read this. And it says, with aldehyde higher priority than alcohol. To understand this statement, let's go ahead and go back to my white screen. There are two types of molecules at this point we're looking at. We're looking at organic molecules, and we're looking at biochem molecules. And specifically, we're looking at the carbs, the carbohydrates. Here is a example of a organic molecule, and these are loose classifications, but just to prepare you for the upcoming tests, I may give you something like this, and I would justify that this is just an organic molecule, not a biochem, because it contains chlorine as well as fluorine. In general, cells do not contain molecules that contain chlorine. Chlorine is actually a poison. This would be classified as just a general organic molecule. I may give you something like this versus this molecule right here. This molecule would actually be classified as a biomolecule. More importantly, it would be a sugar because it contains a alcohol and it contains a aldehyde. You'll also notice the bottom carbon will be connected to a alcohol as well in the condensed form. So recognize the two types of formats. This would be considered a rough organic molecule. This would be considered a biochem molecule. I bring this up because whenever I ask you to determine for monosaccharide biochem molecules, it'll have this format right here, and you may see something that looks like this. Instead of saying the double bonded aldehyde or double bonded carbonyl group in a aldehyde, you may see something like this, where it's summarized as a C, H, and O. And this is code meaning aldehyde. Now, going back to my original reason, oops, I noticed a mistake here. Notice this really should be a wedge. Let me thicken that. There we go. Alright, let's focus on the one on the right side. I made a comment that the aldehyde has a higher priority than the alcohol. So I'm actually referring to this group right here and this bottom group down here. This is what I'm referring to. Now, let me go ahead and erase this part right here, and I'll show you why the aldehyde would be a higher priority. There's a problem when it comes to naming the atomic number. What happens if we have a tie? CH2OH. So notice, we know that the oxygen right here would have the highest atomic number, and that would be the highest priority. If you come over here to the hydrogen, this would be the lowest. But what about this carbon? And what about this carbon? Which would have a higher priority? Well, notice atomic number wise, it's a tie. So if there's ever a tie, you have to go to the next bond. And I'll highlight this in blue, or I'll highlight this in red. So I have to go to the next set of bonds. And I have to figure out, based on these next set of bonds, which one would have the highest atomic number. Now, this is where I mean the aldehyde is more important than the alcohol. Because if I have a carbon double bonded oxygen, and then here I have a carbon with a single bond to an oxygen in this condensed form right here, then the aldehyde would have a higher priority. Here you would just accept it at face value. If you take a traditional biochem course or organic course, we would explain that when it comes to naming these, we think of these as actually two oxygens bonded to this carbon. Don't worry about what I just said. It's not important. Just focus on the idea that when it comes to a tie between the bottom and the top, the aldehyde is the winner. So this would be the second highest priority for this biomolecule, and then the bottom one would be the third highest priority. So now we're going to go here. So in this case, this would be counterclockwise, which would be considered L. However, the wedge is coming out for the lowest priority, so we have to flip it from L to D. Okay, let's go ahead and do this other organic molecule. Here we don't have to worry about that aldehyde issue. So this would be the highest. No, that would be the highest. Fluorine, chlorine. Chlorine would be the highest. The lowest would be hydrogen. Fluorine would be second. Hydrogen, or the oxygen would be third. So oxygen third. So in this case, highest, second, second highest, third highest. So in this case, this would be L form. The hydrogen's coming out. This would be L to D. So I think I beat that to death. So I think I explained this part right here. And please use this as your reference guide. There are many ways to figure out whether you have a D or L enantiomer. In my opinion, this is the easiest once you start practicing it. Let's go straight to my slides. In A, this would be an organic molecule. Let me go ahead and double click this. Actually, let me make this a little bit bigger. So in this case right here, chlorine would be the highest based on atomic number. Fluorine would be second. Oxygen would be third. And then the hydrogen would be the lowest based on atomic number. Notice we're looking at the atoms directly attached to the oxygen. There is no tie, so this one's fairly straightforward. In which case we would go from chlorine to fluorine to oxygen. Chlorine to fluorine to oxygen. So initially we would classify this. If it's clockwise, this would be considered a D. Now, we then need to double check, is the lowest priority going to form a wedge or a dash? So in this case, it's going to be a dash, if I were to draw the wedge dash form for this particular Fisher projection, and therefore it remains D. So in this case, it would still be a D, since hydrogen is a dash. Consequently, this is a D enantiomer. Now, in case you're still practicing your Fisher projection, so the verticals are always going to be dashes, and the horizontal are always going to be wedges, at least for my examples. So here it makes it a little bit easier to see the dashes and the wedges. Consequently, this is a D enantiomer. Technically, the proper term for this one would be D 1 chloro, 1 fluoro, 1 hydroxy methane. That would be the name for this one. Going back to our slides, or actually going back to the screen. So in this case, I could ask you to go ahead and draw the opposite enantiomer in both Fisher projection and wedge dash structures. So, drawing the opposite enantiomer is actually very simple. So by the way, this is going to be a D form. Now I need to go ahead and draw the L form. I need to draw the wedge dash structure and the enantiomer. So what I'm going to do right now is just copy and paste. I start off with the D form, I need the L form. Now what I love about Fisher projection is all you have to do is, if it's in Fisher projection form, simply flip the horizontal groups. So here we have the, oops. So here we have a F, then here we have a Cl. And voila! We now have sketched the opposite enantiomer, the L enantiomer. Let's go to this one right here. Again, I need to go ahead and flip it. F, Cl. I'm going to go ahead and, because I want a duplicate wedge dash, horizontals are wedges, verticals are dashes. Again, if we were to sit there and justify it, it's fairly straightforward. Chlorine is going to be the highest. Fluorine is going to be the second highest. Oxygen is going to be the third highest. Hydrogen is last. And then we would go from chlorine, oops, let me get this out of the way. We'd go from chlorine to fluorine to hydroxy. This is going to be counterclockwise. Counterclockwise, or going to the left, is LEVO, or L, and this would be an L enantiomer. Looking at the last group, do I need to flip it or not? In this case, the last group is a dash, so therefore you do not need to flip. So this is the L form. Whoops. Although it didn't save my changes.